Hello, my name is Ethan Jones. This is my final project for the 2023 spring semester of the class EGR-214 Numerical Methods for Engineers, taught at Cape Fear Community College by Dr. Hans Chapman. This project is a MATLAB function that can calculate the inductance and induced EMF in an ideal solenoid. In this presentation, I will explain the topic further, analyze the code of the MATLAB function, and compare traditional analytical methods with the use of this MATLAB function. To start, we must first explain the topic. Inductance, measured in henries, is the measure of how well a conductor opposes a change in current. To find the inductance of a loop, you can use the following formula, which is the number of turns in the loop multiplied by the magnetic flux over the current. In an ideal solenoid, which is a length of wire wrapped into a tight coil, the magnetic flux can be found with the following formula, which is magnetic flux is equal to the magnetic constant multiplied by the number of turns over the length multiplied by the current and the cross-sectional area of the solenoid. If you combine these two equations, you can find the inductance of an ideal solenoid, which is the magnetic constant multiplied by the number of turns in the solenoid squared over the length multiplied by the area. Electromotive force, or EMF, which is measured in volts, is the amount of energy that is delivered per unit of charge. The EMF in a loop of wire can be found with the following formula, where the EMF equals -1 multiplied by the inductance multiplied by the derivative of charge with respect to time. In the bottom right, there is a figure representing an ideal solenoid. So let's look at an example of how these values could be calculated analytically. Here it states that we have to calculate the inductance of a solenoid that contains 300 turns, that has a length of 25 centimeters, and a cross-sectional area of 4 centimeters squared. So here we have all the values we need to calculate inductance, where N equals 300, L equals 25 centimeters, and A equals 4 centimeters squared. Plugging those into the equation, we get 0.181 millihenries for inductance of the solenoid. Part B of the problem asks for the self-induced EMF in the solenoid, with a current decreasing at a rate of 50 amps per second. We know from the previous part of the problem that the inductance is equal to 1.81 millihenries, and now we know that the charge is equal to -50 t amps, where t represents time in seconds. Plugging these values into the EMF equation and finding the derivative of the charge function, we arrive at a self-induced EMF of 9.05 millivolts. But that method of finding the inductance and EMF can take a lot of time, especially when the values get more complicated and the charge function isn't linear. So here is the code for the MATLAB function that solves it for you. As you can see, this function takes 4 inputs: n, which is equal to the number of turns in the solenoid; length, which is equal to the length of the solenoid in meters; area, which is equal to the cross-sectional area of the solenoid in meters squared; and I, which is equal to the current. It should be noted here that I is inputted as a string of the current equation, where t is the variable. This function then gives 2 outputs. First, L, which is equal to the inductance of the solenoid in henries, and EMF, which is equal to the electromotive force as a function of volts per second, T. It should be noted here that during this presentation, all the examples will give EMF as a flat number rather than an equation of volts per second. This is because in the textbook, none of the problems have a nonlinear charge function, which means that the t gets factored out when taking the derivative. However, this MATLAB function is capable of finding the EMF using any current function, even more complicated ones. Now we can look at the actual code of the function. The first line defines mu, or the magnetic constant. This is equal to 4 times pi times 10 to the -7th. This constant is important when calculating many values related to electromagnetism. Here, we use it to calculate the value of inductance. In the next line, we find the inductance by multiplying that constant by area by n squared over the length. Then we set up t as a symbol, which is used as the variable in both the current and EMF equations. After that, we take the string inputted by the user and turn it into a symbolic function, which MATLAB can use for the remainder of the program. Then, we find the derivative of this function with respect to time. After that, we have everything we need to calculate the EMF. We do this by multiplying -1 by the inductance and then by the derivative of charge with respect to time. We then round that value off to 5 decimal places for convenience. In the last line, we print a simple message giving both the inductance and EMF to the user. The code for this function is simple. but using it we can save a lot of time calculating the inductance and EMF than the analytical methods. To illustrate this, let's look at the example problem from before, but this time solved with a MATLAB function. To refresh, this problem asks us to calculate the inductance of a solenoid that contains 300 turns, a length of 25 centimeters, and a cross-sectional area of 4 centimeters squared. Then we are asked to calculate the self-induced EMF in the solenoid if the current it carries decreases at a rate of 50 amperes per second. From this question, with a few unit conversions, we can get all the inputs we need to use our function in MATLAB. N is equal to 300, length is equal to 0.25, the area is equal to 0.0004, and the current is equal to negative 50 times t. When inputting this into the function, we get the result shown here. Inductance is 0.181 millihenries, and EMF is 9 millivolts. Comparing this to the results we got earlier, we can find that they are identical. Let's look at two more problems to show how useful this function can be. In this problem, we are asked to find the inductance of a coiled telephone cord if the wire has 70 turns, a diameter of 1.3 centimeters, and a length of 60 centimeters. Analytically, we can find the area by multiplying pi times the radius squared. This gives us the cross-sectional area of 0.00013 meters squared. We can then find the inductance by multiplying the magnetic constant by that area by the number of turns squared over the length. After calculating this, we arrive at an inductance of 1.334 microhenries. In MATLAB, this solution is even easier to come across. First, we find the area, just like in the analytical solution. Then we have all the inputs we need to calculate inductance. Simply input the number of turns in the solenoid as 70, the length as 0.6, the area as 0.00013, and the current function as 0, since there is no change in current. After putting this into the function, it gives us the inductance as 1.334 microhenries, the same as what we got using analytical methods. But let's look at another example that asks for both inductance and EMF of a solenoid. In this problem, we are asked to find inductance in a solenoid with 580 turns, a length of 36 centimeters, and a cross-sectional area of 50 centimeters squared. Then we are to find the EMF generated if the current is increasing at a rate of 4 amps per second. Analytically, we must first find the inductance by multiplying the magnetic constant by the area by the number of turns squared over length. Once those calculations are finished, we find that the inductance is equal to 5.87 millihenries. Now we can find the EMF by first finding the derivative of the charge function, which is simply equal to 4, and then multiplying that by negative 1 and the inductance of the solenoid. Doing that, we can find that the EMF of the solenoid is negative 23.5 millivolts. Once again, however, these same numbers can be found even easier using MATLAB. Simply call the function, inputting n as 580, length as 0.36, the area as 0.005, and I as 4 times t. Immediately, the function will give you the inductance of 5.87 millihenries and the EMF as negative 23.5 millivolts. Once again, this is the same as what we got using the analytical methods. To conclude this presentation, it is important to note that ideal solenoids are a good approximation of inductors, which are one of the 3 basic circuit components that make up the foundation of modern electronics. Inductors play a key role in radio equipment, energy storage, induction motors, and sensors. When 2 inductors are placed in sequence, they can form a transformer, which is a fundamental component of the power grid. With this MATLAB tool, one could approximate the inductance and induced EMF in any inductor just by counting the turns and measuring the length/area without needing to do any complex calculations or derivatives. This ultimately saves engineers both time and money without losing accuracy. Thank you.